All right, when we introduce the idea of quantized energy levels and quantized energy in terms of photons, we introduce this concept of wave-particle duality. That is, in considering the properties of light, we needed to consider both its properties as light traveling as a wave, but also as its particle-like properties, light coming in discrete photons or discrete packets of energy. Well, it seemed reasonable that if light has wave-particle duality, it seemed reasonable to ask whether or not we also need to think of matter as having both wave and particle properties, that is, wave-particle duality. And in fact, there was a significant amount of evidence that indicated that this may be the case. Okay? And a gentleman by the name of Louis de Broglie actually demonstrated that we can describe the wave properties of matter using this equation. That is, for a particle, we can describe its wavelength, what we call the de Broglie wavelength, is equal to Planck's constant divided by the mass times the volume, or the momentum of the particle. Okay, and so this will allow us, for any given particle at a particular mass and a particular speed, will describe its wavelength. That is a wave-like property. Now, it turns out that these wave-like properties are only really significant when we're dealing with really, really small particles. And so let's sort of do a couple of simple examples here to give us a sense for the significance of this. So let's first start by talking about a classical particle like a baseball. Okay? So a baseball weighs approximately 5 to 5.5 ounces, and if we throw that baseball really fast, a good fastball is around 95 miles an hour, which corresponds to 42 meters per second approximately. Okay, so if we wanted to calculate the wavelength of this particle, we would say that lambda is equal to h over mv. So h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And when we use joules here, we have to include our mass in kilograms. So a 5-ounce baseball is around 0.145 kilograms, so 0.14145 kilograms. And then our speed here, our velocity, is 442 meters per second. So when we do this calculation for a baseball, we find that the wavelength, lambda, in meters comes out to something like 1.1 times 10 to the minus 34 meters. Okay? And when we look at a number like this, that's a really small number. And so when we think about the properties of a baseball is certainly a large object, and this sort of a wavelength really is completely insignificant relative to the size of a baseball. And so when we think about the properties of baseballs, or really any other large object, anything you can see, the wave-like properties are completely insignificant. They have no effect on our ability to understand the motions or the behavior of that object. However, when we are looking at something like an electron, okay, so for an electron, we have the mass is equal to 9.108 times 10 to the minus 31 kilograms. That's the mass of an electron. Okay, and if we imagine this electron is traveling at a relatively rapid rate, let's say it's traveling at about 0.5% of the speed of light. So we're going to just make an estimate that we have an electron traveling at 1.5 million meters per second. Okay, so this might be an electron traveling in a beam or something like that. When we calculate lambda for this electron, we again put Planck's constant, joule seconds. We divide by that mass, 9.108 times 10 to the minus 31 kilograms, and its speed, 1.5 million meters per second. Okay. Now when we calculate the wavelength of this electron, we are dealing with wavelengths on the order of 4.8 times 10 to the minus 10 meters. So when we do this calculation, we find that the wavelength for an electron traveling at a relatively high speed has a wavelength of about 4.8 angstroms, or 4.8 times 10 to the minus 10 meters. And now when we think about this wavelength, and whether or not this will affect the behavior of this electron, we go back to our understanding of our atomic model, right? We know that the nucleus is much larger than an electron, right? A proton is on the order of 2,000 or 1,800 times more massive than an electron. So an electron is really small compared to a nucleus, and your typical atom runs in the range of 1 to 5 angstroms in diameter, right? So if we think about the size of an atom, that is right around in the magnitude of the size of the wavelength of this electron. That is to say, this wavelength is much, much larger, by many orders of magnitude, much larger than the size of an electron. So when we want to consider the properties of an electron, we really need to take into account these wave-like properties. That is, the behavior of an electron or other very small particle behaving as both a particle and a wave. Okay? Now, this idea that electrons have wave-particle duality led to a bit of a problem in the development of quantum mechanics and certainly in our understanding of the model, right? Because Niels Bohr suggested that these electrons travel in very discrete shells. That is, we could define a nice, clean orbit or a shell around the atom within which this electron is traveling. But now we've said that there are these wave-like properties, that there are very large wavelengths of the electron relative to the size of that electron. And that led us to basically be unable to say precisely at a given time where the position of that electron may be. Okay, and that is something that is very commonly called the Heisenberg's uncertainty principle. Okay, and what this says is that we cannot determine exactly the position, the direction of motion, and the speed of an electron simultaneously, or really any atomic particles. Okay, so therefore we can't really say where that electron is relative to, say, the nucleus of an atom. Okay, and so Bohr's very elegant and simple model that explained the line spectrum of hydrogen really is inconsistent with this. That is, we just can't say where that electron is, that it exists within a particular shell at a particular energy level. Okay, and mathematically, what this principle says is that there is uncertainty in both position and momentum, and that this product must be greater than Planck's constant over 4 pi. So again, it really only applies to things very small, like an electron. So this posed significant problems in our understanding of our model of the atom, and it certainly put a great deal of skepticism into this very simple Bohr's model. Now, because we could not determine exactly where an electron is, Erwin Schrödinger suggested that even though we can't know exactly where it is, we do, in fact, know that that electron exists. So even in the hydrogen atom with that one electron, we can't say that that electron is in a 1s shell or a 2s shell, but we can say that that electron exists, and it has a high probability of existing very close to the nucleus, that is, within the volume of the atom. And so instead of treating the electron as being present in a very particular spot or traveling in a precise path, Schrödinger introduced a statistical model in which he devised an equation that would allow us to calculate the probability of finding an electron within a particular region of space with respect to the atom. Okay, and this is known as Schrödinger's wave equation. And we're not going to go into these types of calculations. Some pretty sophisticated mathematics is required. But basically, Schrodinger's wave model is based on an equation that contains both wave and particle terms as well as energy terms. Okay? And the important thing about this equation is that it defines the wave parts of these electrons in terms of something we call a wave function. And when we solve the equation for this wave function, it gives us the shape of a three-dimensional region of space within which there is a high probability of finding that electron. And we call these solutions, these regions of space, we call these orbitals. Okay? And we're going to, in our next quick video lesson, we're going to talk about what these different types of orbitals are, but basically this is the idea. We say we can define a region of space, and here is a circular region of space that we might imagine has three dimensions, so it's spherical. We can say that within some defined limit, represented by this red line, within that limit there is a high probability that the electron exists somewhere within this region of space. That is to say, it is more likely that that electron is somewhere in here versus somewhere way out here. Okay, and so we define orbitals as a region where there's a high, 95% or greater, high probability of finding that electron within this area. And sometimes we think of this in terms of electron clouds. But really these clouds are regions, so these orbitals are regions of high electron probability density. That is, it's a region in which there's a high probability of finding that electron. So these electron clouds really are regions of high electron probability density. So the more dense these clouds, the higher that probability. So that's all these orbitals are. It's just they're a region of space that describes where we expect to find that electron. It doesn't say that the electron is, say, right here. It doesn't say it's here. It doesn't say it's here. What it does say is it is probably not out here or here or here or here. Okay, it's somewhere within this region of space. We can't say exactly where, but we know it's somewhere in that region.